So, welcome my friends, welcome to my next lecture. So, this lecture I am planning to finish the notions of curl and Laplacians. Of course, in fact this topic I should say gradient divergence I already discussed in my last couple of lectures. Already I introduced the notions of curl. Today I will just recall the definition of curl and couple of properties I will talk about, and then at the end I will talk about Laplacian. So, I think by this lecture, by today's lecture I will finish all those concepts. Okay. So, as I said, so I already discussed the notion of curl in my last lecture. So, what is curl? If you remember, if I have a vector field capital F, okay, suppose nice vector field, and if I have a operator del operator, right. So, that means del x1, suppose if I have a vector field F from some domain D subset of Rn to Rn, then curl is nothing but if I have a del operator which is nothing but del x1, del x2 up to del xn, that n tuple. And if I have the vector field capital F, suppose it has a component small f to up to small fn, then curl is nothing but that this one. If you remember, that means this cross f, this is the one. So, this vector field, okay. So, that is known as curl. So, I talked about already, I discussed about the interpretation of curl. Let me just recall once again. So, what is the interpretation of curl? So, maybe I think I should say that what is the definition of curl. For example, this is the one, right, curl of a vector field, right. If I have a vector field capital F, okay, then curl of F, this is the notation curl bracket F, which is nothing but this what is called your operator del cross F, and that I know you know the cross product, the definition of cross product I already explained. So, which turns out that this is the corresponding vector I am talking about, curl of F. So, that means if I have a component capital M, capital N and capital P corresponding to my vector field capital F. So, this is the corresponding component of curl. This is the first component, that means del P del Y minus del N del Z. Second component is del P del X minus del M del Z, and third component is del N del X minus del M del Y. Okay. So, then couple of properties, like it behaves like a linear operator A plus BG. If I have two vector fields capital F and capital G, then A will come out, you have curl of F plus B times curl of G. That means curl is a linear operator. And if I take a scalar field small f, and if I have a vector field capital F which I started with, then if I take the curl of the product, scalar field times vector field, then actually this kind of Leibniz rule you might say. So, it is f times curl of F plus gradient of F cross F. So, now is the interpretation of curl, as I said. So, curl has to do with how its direction changes. So, it changes the direction. So, curl has something to do, that means if curl is there, then there is a changes of directions. Okay. So, this is the number one. Second one is curl of a vector field represent rotational motions. That means if there is a positive curl, then it represents that corresponding vector field has a rotational motion. Okay. So, the third one is that I have written the curl measures the tendency of the vector field, to curl around a given point in a directions given by the right hand rule. Right hand rule means what? So, look at this one. So, this is the suppose the directions, right. So, what I will do in the directions, I will put my finger, and the thumbs which is the upperwards, that is like kind of directions of the curl. Okay. So, that is exactly I have written that the curl measures the tendency of the vector field to curl around a given point in a directions given by the right, that is the right hand rule actually. So, in the directions you put your finger, and this is the thumbs will be in the upper hand, that is called the directions, or right hand, I should say the right hand rule. Okay. So, also there is a note. So, curl is simply the circulations per unit area or circulation density or rate of rotations, that means amount of twisting at a single point. Okay. So, I tried to give some kind of pictorially, like suppose this is your vector field, suppose this is my vector field, and suppose you have a paddle wheel, suppose this is my paddle wheel. Okay. So, to measure the spin. Okay. And this is the corresponding right hand rule. Okay. So, if there is a spin, that means suppose this is my directions. So, what you have to do, you have to just in the directions you put your finger and thumbs, what is the direction is in the upperwards. So, that kind of behaves like curl. So, in other words, I said that if the paddle, so this is the corresponding paddle, if the paddle does turn, if it turn, okay, it means that this field has a curl at that point. So, that means if that field has a curl, non-zero curl at that point, that means that paddle does turn. On the other hand, if it does not turn, then I will say that there is no curl. Okay. So, that means if the field corresponding that point has a curl, that means non-zero curl, that means the corresponding paddle actually does turn, and if it does not turn, that means curl is actually 0. Okay. So, that is the kind of interpretation of curl. Now, let me see the another notions. Once I have the notions of curl of a vector field, then I can talk about what is called irrotational vector field. Now, you see earlier on I said that curl of a vector field represent rotational motion. So, that means that is the interpretation. That means if I have a non-zero curl, so it will represent the rotational motions. So, it is expected if I want to talk about the irrotational, that means curl should be 0. That is the natural kind of thing you might think about that. Okay. So, curl represents rotational motions. Curl of a vector field represents a rotational motion. So, now if I want to talk about irrotational kind of things, that means curl has to be 0. And it is indeed the case. So, this is the definitions. A vector field capital F in R3 is called irrotational if I have the curl of this vector field F is 0. Okay. So, as I said, so if given a vector field capital F, if curl of F is 0, then I will say that that vector field is called irrotational. Okay. For example, like physical example, in case of fluid flow, if curl of this vector field F is 0, that means that the flow is free from the rotational motions. It is expected, right? Because curl of F gives the rotational motions, right? That is exactly I have said. So, curl of a vector field, this is on curl of a vector field represents rotational motions. So, therefore, if I talk about curl of F is 0, so that means the flow is free from rotational motion. That means there is no whirlpool. So, that is what it is. Okay. So, this is the kind of physical example. So, in case of fluid flow, if curl of F is 0, it means that the flow is free from rotational motions, that means no whirlpool. Okay. So, one example I have given. So, if I just take a vector field like capital F of x y z, which is x I cap, y j cap and z k cap. So, that means it is a vector field capital F from R3 to R3. This is the vector field, right. So, it maps F of x comma y comma z to x comma y comma z. So, now what is the curl? If I calculate the curl, so that means this is the formula, that means this is like del cross F, okay, and this is the corresponding determinant formula. So, what is that? The first row it is I j k, second row it is nothing but del del x, del del y, del del z, because I am in R3, and third one is the component. So, that means component of capital F. Now, capital F is a map from R3 to R3. So, what are the components? This is F1, this is F2, this is F3, right. So, that means F1 is nothing but the functions. So, what is this F1? So, F1 of x, y, z, this is nothing but x, F2 of x, y, z, which is nothing but y, and F3 of x, y, z, nothing but z. That is the corresponding scalar field, right. So, that means this x, y, z. And you just calculate the determinant formula. That means what will happen? First one is the I cap times del z del y minus del y del z, and which is what? Which is 0, because I am taking the derivative with respect to y variable of z. So, that means this is 0, that is also 0. So, therefore, this is a 0 plus or minus j cap. What will happen? Del z del x minus del x del z, that is also 0, and plus k cap. What is del x del y del x minus del x del y. So, all of them equal to 0. So, this is 0, this is 0, this is 0. So, therefore, the curl is 0. Okay. Since the curl of this vector field is 0, so therefore, I say that this vector field is rotational in the what is called R3, in R3, 3-dimensional Euclidean space. Yes. Okay. So, now couple of more examples I have given. Okay. So, what are the examples? So, first example says that if I have the vector field which is capital F of x y z, it maps only 0 0 comma z. So, that means this is the vector field, right. So, F is a map from R3 to R3. Okay. So, x y comma z maps to 0 0 comma z. So, that is the vector field. Okay. This is the one. And of course, if I just calculate the curl, of course, curl of F is 0, that means everything, this component is 0, and of course, it is like x y z earlier one. Here x is 0, y is 0. So, therefore, curl of F is 0, and hence capital F is irrotationals in R3. Now, this is second example. If I consider the vector field, what is called capital F x comma y comma z, which is x times, you see now this time what is x comma z cap. So, that means what is this? This is, if I write it, what is the vector field? Capital F from R3 to R3, and capital F of x comma y comma z. What is the map? X times j cap. So, that means in the second component you will have x. So, therefore, 0 comma x comma 0. This is the one. Okay. Now, if you just apply the what is called determinant formula, that means what is the determinant formula? I cap, j cap, k cap, then you have del del x, del del y, del del z. Okay. And what will happen? First, this is 0 functions f1, this is small f1, this is small f2 and this is what? Small f3. So, this is x and this is what? 0. And if I calculate it, what will happen? I cap, the corresponding coefficients of I cap, with this 0, if I take the 0, so if I take the del z of x, that is also 0. What will happen in the this one will survive, you see. So, first one is the I cap, right, which is nothing but del 0 del x minus okay, I cap, right, and del 0 then del x del z. So, this is 0. Now, this one will survive, minus j cap. Minus j cap means what? So, this, so that means no, that will also not survive. So, that will also be 0. So, I mean this is del 0 del x minus del 0 del z, that is also 0. So, let us see the k cap. K cap means this and this. So, that means yes. So, that means this is del x by del x minus del 0 del y. So, that means it will give you actually k cap. Okay. And that exactly I have written. So, curl of f is exactly equal to k cap, which is not 0, and therefore, my corresponding vector field is not irrotational in R3. Okay. So, you have to just calculate the formula, you know the determinant formula, you just calculate, that means you have to just identify what are the small f1, small f2, small f3, that means what are the components of my vector field capital F, use the determinant formula, calculate it, calculate the coefficients. So, if you just very simple in this case, because the what component functions are almost very simple component functions. So, therefore, this is the if we take the calculate the curl, it is k cap, so it is not irrotational. What about the third example? So, again this is kind of rotational kind of things, right. So, it is expected curl should be non-zero, right. Rotational means curls, that is the kind of implications, curl that says that if curl is non-zero, then there should be a rotations kind of things. So, it is quite clear, because now I am in R3. So, but still the look at that like kind of this kind of definition you have seen already, f of x y goes to minus y comma x from R2 to R2, right, that is rotational, right. So, here actually what is the map? It is actually x comma y comma z maps to minus y comma x, and then z component is actually 0. So, and if I calculate the curl, I am not doing it actually, you just do that. As I said, component functions are very nice. So, what is the component function? First component function, that means small f1 is minus y, small f2 is x, and small f3 is 0. You just calculate the determinant. So, curl of f turns out to be 2 times k cap, and therefore, it is non-zero. So, therefore, f is not irrotational. So, it is expected, I know that rotational kind of things. Okay. This is the third one, and what about the fourth one? Again it is a vector field. Again, what are the component function? You can write it. So, f of x comma y comma z, what is the map? X y comma minus, okay, I think there is a mistake here. Yeah, I think this should be sin z. So, there is a z missing. Okay. So, sin z, okay, it is sin z comma y. Okay. So, this sin z is missing. So, this should be sin of z, z is missing. Okay. So, this is the one. So, that means what is my, this is my small f1 function, this is my small f2 function, this is my small f3 function. You just use the formula, then it will be very easy. So, what is the formula? You have I cap, j cap, k cap, okay. Then you have what? Del del x, del del y, del z, correct. And what will have? You will have x y, you have minus sin z, and then what will have? 1, okay. And you just use the formula, that is it. So, if you just calculate it, what it turns out that curl of f is this one, and again it is non-zero. So, therefore, my vector field capital F is not irrotational vector field in R3. Okay. So, these are a few examples, you just use the formula. I am not doing it actually, because it is very simple. You have to just calculate this formula. Okay. So, that means I cap, that means del 1 del y, which is 0, then del z, that means what will happen? Minus minus get cancelled, that means cosine z times I cap, and that is exactly this one. So, that means you can do that, not an issue. So, I cap means what? So, that means this you just omit it. So, that means del del y of 1, which is 0, then there is a minus sign, minus minus get cancelled, that means derivative of sine, which is nothing but cosine. Done. What about minus j cap? Minus j cap means this. So, that means del del x of 1, which is 0, and del del z of x y. Now, I am talking about the derivative with respect to z variable of the function x y, that means it is independence of z. So, therefore, this is also 0. So, it will not contribute anything. And what about k cap? K cap will be this and this. So, that means you will have del del x of minus sin z, again it will be 0, minus of del del y of x y. So, if I take the derivative of x y with respect to y variable, then x will be there with a sign minus x. So, that means cos z times I cap minus x times k cap, which is nothing but this one. Okay. Very easy. Okay. So, now there is a concept called gradient field is irrotational. So, gradient field we know, I will show that gradient field actually irrotational vector field. Okay. So that means curl actually 0, that is what it says. Okay. So what is the theorem? I write it as a theorem. So let small f be a C2 scalar field. C2 scalar field means what? That means it is twice continuously differentiable. Okay. So that means it is a scalar field. First of all, it is a map from say R3, I am restrict myself. So some domain D R3 to R. It is C2 means it is twice continuously differentiable. Then the gradient vector, of course, if I have a scalar field, if I take the gradient, it will be a vector field, right? That is called the gradient vector field. So what is my del f, which is nothing but fx, fy, fz, that means del f del x, comma del f del y, comma del f del z, which is irrotational. Irrotational means what? If I calculate the curl of this vector field, it turns out to be 0. So if I calculate, that means curl of del f is 0 in that domain. The proof is very simple. What is the proof? You have to calculate the curl of del f. So this is my vector field. So that means what you have to do? You have to curl, it means you know that is the del operator cross your vector field capital F, which is nothing but del f. So then what is the formula? So formula is this one, I cap, j cap, k cap, that is the first row. Second one is del del x, del del y, del z, del operator, and third one is the vector field. And what is my vector field? Because it is a gradient vector field, so that means what are the components? Del f del x, del f del y, and del f del z. Then it is 0. Why? That is very nice, right? Because if I take the I cap, just calculate the one component. So if I take the I cap, then what will happen? You just omit this one. So you will have del 2f del y del z minus del 2f what is called. So I think I should not write in this way, then it is more clear. So I cap, okay, I should, what is this? So that means I cap, you will have del y of del f del z minus what will happen? Del z of del f del y. Okay. So this is the actually mixed partial derivative. So first I am taking the partial derivative with respect to z variable, and then I am talking about the derivative with respect to y variable. And what is going on here? So that means first I am talking about the y variable and then z variable. So that means this is mixed partial derivatives. But what is this? I already kind of explained this kind of things. If I have a scalar field and if it is all the second order partial derivatives, they exist and continuous, then all the mixed partial derivatives, they actually equal. So that means del 2f del y del z, which is exactly equal to del 2f del z del y. That means this is equal to this, that means this component will be 0. Okay. So that is why C2 part is very important. Since I assuming that my scalar field small f is in C2, that means all the second order partial derivatives, okay, exist and they are continuous. That means mixed partial derivative exist and they are equal. Okay. So therefore each of the component, like I component we have the mixed partial derivatives. Similarly you can calculate the component of j cap, again it will be a mixed partial derivatives of like with respect to xz variable. So first z then x, or first x and then z. So both are same. Similarly if I take the component of k cap, that means it will be partial derivative, mixed partial derivative with respect to xy variable. That means I am doing the partial derivative first y variable then x, or first x variable then y. But anyway, all the mixed partial derivatives, since they are continuous, so they are equal. So therefore all the component of I cap, j cap and k cap 0. So therefore curl is 0, and therefore the corresponding gradient vector fields actually irrotational. Okay. So assumption is very important. So that means it should be C2 scalar field. That is the very important assumption. Okay. So this is nice. That means if I have a gradient vector field with the scalar potential f is in C2, then this vector field or gradient vector field is actually irrotational. So what is the equivalent statement? Okay, I have written, right, because the mixed partial derivatives of are equal. What is the equivalent statement? That let capital F be a vector field in some domain D in R3. On D, if curl of f is non-zero, that will implies that f is not conservative or gradient. Well, yes, I just observed that if my f, capital F, that means the vector field I am started with, if that vector field is not conservative or gradient vector field, that means curl has to be 0. Just now I observed, right? If I have a capital F is very nice vector field or gradient vector field with scalar potential is C2, that means if I have a gradient vector field with scalar potential is C2, I just observe that curl has to be 0. So therefore if curl of F is non-zero, it always implies that my vector field capital F, which is not conservative or gradient vector field. That is the first observation. And that there is a note. It says that now if suppose, that means what? That means curl of F is non-zero, it implies that my vector field is not a gradient vector field or conservative vector field, right? However, if curl of F is 0, you should not think that okay, it always implies that F is conservative. Okay. So curl of F is non-zero, it implies that F is not conservative or gradient vector field. But what will happen if curl of F is 0? Will it imply that my vector field always gradient vector field or conservative? Answer is no. So, curl of f0 does not imply, I will talk about some examples, that curl of f is equal to 0 does not imply always that your vector field is gradient vector field or conservative vector field. That means, I will have examples of what is called gradient vector field and vector field which is not conservative, but still curl of f is 0. So, that kind of examples available, I think. Okay, let me see, I think in the next slide it will be there. Yeah, so okay, so this is, so recall example, I think this example I already discussed. So, this is non-conservative field, that means the corresponding what is the conservative vector field? If you remember, if I have a domain and if I take a simple closed piecewise smooth closed curve, then if I consider the vector line integral, it has to be 0, right? That is the meaning of conservative, right? But this kind of vector field is not conservative in that domain. That is very important. Means if I take out the origin from R3, this kind of vector field is actually not a conservative vector field. In fact, that vector line integral is non-zero. However, so f is 0 in this star. Okay, f is 0 means I think curl of f is actually 0. So, if I take the curl, okay, I think maybe let me just go back. I think I have done it. Yeah. So, conservative means what? If I take every piecewise smooth oriented closed curve, the vector line integral should be 0. Now, look at this one. Let's see. Of course, it is in 2 variable, but there is one more R3 to R3. So, but again you do the same process, you will see end up that this vector line integral is 2 pi, which is non-zero. That means, it is not conservative, okay, in that domain. Here I am in R2, there I am actually talking about R3 minus, but same calculation will work, you do not worry. Okay. So, therefore, first observation is that f is not conservative vector field in my domain D star. However, I think this is f is 0 means it is wrong, curl of f, this should be the case. Okay. So, you just calculate the curl of f. Again, this is the determinant formula. First row is I cap, j cap, k cap. Second one is the del operator, del x, del y, del z. And what about the capital F component? You just write it. What is capital F? It is very nice. F of x y comma y comma z. So, first one is minus y divided by x square plus y square. Second one is x by x square plus y square. And third one is 0, right? Because there is no component in k cap. And you just perform the derivative, that is it. Only thing is that it will be like k cap times this one. So, therefore, this is actually turns out to be 0. Okay. Of course, I cap, if I take the I cap, because this is 0, right, and of course, this is 0 because this one is independent of z, right. What about j cap? So, that means again this is 0, del x of 0, and again if I take the derivative del z of this one, that is also 0 because there is no variable in z. So, only the k cap will survive. So, if I take k cap, that means del x of x by x square plus y square, this is the one, and then you have del y of minus of this one, and if you calculate it, it turns out to be that this is also 0. So, therefore, curl of f is 0. Okay. So, now I have an example of a non-conservative vector field, still my curl of f is 0. So, therefore, this is the conclusion. So, curl of f is 0 does not always implies that my vector field capital F is conservative and gradient. However, if curl of f is non-zero, it always implies my vector field is not conservative of gradient because of this theorem. Because if I have a nice scalar field which is C2, and if I consider the corresponding gradient vector field, his curl is always 0. Okay. There is a notion of what is called scalar curl. Okay. What is the meaning? So, if I start with a vector field capital F from some domain subset of R2 to R2 with the component is capital M and capital N, then by identifying F in R3. Now, if I have a vector field in R2, how do I identify in R3? Just by considering the z component is 0. So, that means exactly I am writing. So, I am just have the vector field capital F in R2, then I am thinking that F in R3 by keeping the z component is 0, that means this is the first component, this is second component, this is third component. One can get curl. Now, you can, if you calculate the curl, it turns out that this is nothing but the corresponding curl of this vector field capital F in R3, okay, whose component is, first component is capital M, second component is capital N, and third component is 0, like the earlier one, the same thing. Okay, if you just calculate it, you will end up with this kind of object. So, because what? This is I cap, this is j cap, this is k cap, right? And then what will happen? Del x, del y, and del z, right? And what was the first one? Mxy, then you have nxy, and third one is 0. Okay, you have to calculate this one. Now, what will happen? There will be no coefficient of I cap. Why? Because if I have I cap, then del y of 0, it is 0, and del z of nxy. Now, capital N is a function of xy. So, there is no variable in z. So, therefore, this derivative is also. So, there is no contribution in I cap. What will happen in the j cap? Same thing. Del x of 0 means it is 0, and what will happen? Del z of capital M x y, again it is a function of x and y. So, no variable in z, so therefore, this is 0. So, only k cap will survive, which is nothing but del n del x minus del m del y, which is nothing but I have written. So, therefore, if I have a capital F or vector field whose components capital N and capital N in R2, I can identify that capital F in R3, and if I calculate the curl, which is exactly equal to this one. So, then I am saying that, so let capital F, which is capital M I cap plus capital N j cap for x y is in R2, define the scalar field G on D by G of x y, which is del n del x minus del m del y. I am defining the scalar field on my domain D subset of R2, then the G x y, this function is called the scalar curl of the vector field capital F M comma n. Okay. So, that is the definition. So, that means what I am doing, I am starting with a vector field capital F in R2, then I am looking at that capital F in R3, I am calculating the curl. So, it turns out that it is nothing but del n del x minus del m del y times k cap, and coefficient of I cap and j cap is 0. Then I am doing that, okay, define a function g, small g from my domain D subset of R2 to R, which is nothing but this is the kind of objects, I mean del n del x minus del m del y, and this is nothing but the scalar curl of the vector field capital F in R2, that means m comma n. Okay. So, for example, I have given the scalar curl of the vector field minus y square comma x, you just calculate it, g of x y should be 1 plus 2i, and that is okay, you just calculate del n del x. So, this is my n part and this is my m part. Okay. So, what will happen, del n del x, so del n del x, that means it will give you 1 and minus, so minus minus get cancelled, that means you 1, and I have to take the del m del y, I mean 2y. So, this is very simple. Okay. So, this is the scalar curl of the vector field capital F, which is of the form minus y square comma x. Okay. So, couple of concepts. So, let v comma x y or v of x y denote the velocity, some real life applications. Okay. So, let v x y denotes the velocity field of the fluid over a plane region in R2. Okay. So, let v comma x y denote the velocity field of the fluid over a plane region in R2 in case of incompressible fluid. So, that is a definition. So, if the divergence of my v is 0, that means if the divergence of the vector field is 0, then I am saying that this is incompressible fluid. Okay. First one is that the scalar curl, if I calculate the scalar curl measures the rate of fluid's rotations at a point. Okay. So, now I have a vector field F in R2. Now, I have the notions of scalar curl. So, I am talking about the implications of scalar curl in this concept. So, it says that if I have a vector field, that means if I have a velocity vector field of my fluid over a plane region in R2, and in case of incompressible fluid, that means if the divergence of that vector field is 0, then the scalar curl measures the rate of fluid's rotations at a point, number 1. Number 2, the scalar curl is positive at a point, okay, where the rotations is counterclockwise. Okay. And the scalar curl is negative at a point where the rotation is clockwise. So, these are the kind of implications of my scalar curl. So, that means you have start with a velocity vector field of the fluid over a plane region. Suppose it is incompressible fluid, that means divergence is 0. Then the scalar curl measure the rate of fluid's rotations at a point. Okay. Now, if the scalar curl is positive at points where the rotation, if the rotation is counterclockwise, that means the scalar curl is positive, and if the what is called rotation is clockwise rotations, that means if the clockwise rotation, that is the scalar curl is actually negative at the points. So, that means if the what is called rotation is clockwise, then the corresponding scalar curl is negative, and if the rotation is anti-clockwise, then the what is called scalar curl is positive at that point. So, that is the kind of implications. So, now I define another concept, what is called vector potential. Okay, scalar potential, you know, right? If I have a scalar field, nice scalar field, then I have a gradient vector field and the corresponding small f. Suppose you have a scalar field small f, then you can take the gradient of that, it will become a gradient vector field, and that small f is called the scalar potential. Then I can have the notions of what is called vector potential. What is the definitions? Vector field capital F D, again I am in actually 3-dimensional Euclidean space. So, a vector field capital F in the domain D subset of R3 is said to be a vector potential if there exists a vector field capital G such that, well, that is very nice, you can have your capital F if I take the curl of G. Okay. So, that means start with a vector field capital F in some domain subset of R3, I will say that that vector field is said to have the vector potential if I have another vector field capital G, if I take the curl of G, it should coincide with my vector field capital F, which I started with. Okay. So, that is the definition. So, a vector field capital F in the subset of R3 is said to have vector potential if there exists a vector field G such that if there is a vector field G in D such that if I take the curl of G, which is exactly coincide with my vector field capital F. For example, let us see one example, right. Like for example, what is my gradient vector field, if you remember. Gradient vector field means what? So, a field vector field capital F, say in R2 or R3, I will say that this is a gradient vector field if there exists a scalar field, say from R2 to R or R3 to R, such that if I take the gradient of F, then it becomes a vector field, and that vector field is exactly equal to the capital F, which I started with, right. Then in that case, that vector field, I am saying that this is actually a what is called scalar gradient vector field, and small f is called the scalar potential. Now, same notion, similar kind of notion, same, now I should not say same, but similar kind. So, I have a vector field capital F, I am saying that it is said to be a vector potential, okay, is said to have, that vector field is said to have a vector potential if there exists another vector field capital G on that domain D, such that if I take the curl of G, would is actually coincide with my vector field capital F. If this is the case, then I will say that my vector field capital F is said to have the what is called is said to have the vector potential. One example, suppose the magnetic induction field capital B associated with a current in a wire is given by this. Okay. Suppose you have a magnetic induction field capital B, which is associated with a current in a wire, and suppose B is given by x comma y comma z, which is nothing but I times, this is the first component, this is the second component. Okay. And of course, third component is 0, because this is, you can see, you can have it plus 0 times k cap, where I is some constant. Now, if I consider this vector field capital G, which is minus I by 2 ln of x square plus y square times k cap, okay, then if I calculate the curl of G, curl curl of G, then you will have B. So, therefore, G is a vector potential for B. Okay. So, this G, the vector field you will have such that if I take the curl of F, then G is called the vector potential of capital F, or a capital F has a vector potential, and what is that vector potential? Is vector potential is capital G. So, that means you just calculate the curl of G, that means you just calculate this one I cap, j cap, k cap, okay. Then you have del del x, del del y, and del del z, right. And what is the first component? So, that means this is, what is this component? So, that means you have 0 0 and minus I by 2 ln of x square plus y square, that is the component, right. So, this is what 0 0 and this minus I by 2 ln of x square plus y square. Okay. So, that is the thing you have to calculate. Okay. So, therefore, you just calculate what will be my I cap. So, if I calculate the I cap, so that means this is that means I have to take the del del y of this one minus I by 2 times ln of x square plus y square. Okay. What is the derivative if I take this? Because this one is 0, del z of 0 is 0. So, therefore, you just take the derivative. This is I cap. So, that means, well, I should say minus I by 2 will come out times I cap, and then I have to take the partial derivative of ln of x square plus y square with respect to y variable. That means, what will happen? 1 by x square plus y square as it is, and then you will have 2y. Okay. And what is this? That means 2 get cancelled, then this should be minus, I should say I cap as it is, okay, and this should be minus I y by x square plus y square. Okay. That is the first one. This is the component survive with I cap, and we see I cap, what is the component of I cap? This is like minus y divided by x square plus y square times I, this I is there, and similarly you just calculate the j cap. So, j cap means what? J cap, what is this? J cap means, so minus j cap, you can write it. So, minus again del del x, sorry, this, yeah. So, this that means you have del del x of minus I by 2 ln x square plus y square, this one, and this one will be 0, del del z of 0. So, 0. So, what is this? This is minus j cap. We just do the same calculation. I think this minus and this minus will get cancelled. So, you will have actually j cap times x by x square plus y square times I. Now, if I take I common from here, what will be the first component? Minus y by x square plus y square, and second component is x by x square plus y square. So, therefore, your B, the vector field, which is nothing but like curl of G. So, therefore, the vector field capital B has a vector potential, and what is my vector potential is capital G. Okay. So, this is a simple example, like in the gradient vector field, this is corresponding. For gradient vector field you have a scalar potential. Now, for this vector potential means start with a vector field, get another vector field, if I take the curl which should exactly equal to the vector field we started with. Okay. There is a theorem, divergence. If I have a curl, so if I take the divergence, then what will happen? So, this is I put it as a theorem. So, let capital F be a C2 vector field, I am assuming, that means twice continuously differentiable. Then this is the formula, you just can calculate it. So, if I have a curl of capital F, so that means it is against a vector field, and if I take the divergence, it turns out to be 0 actually. That is what it says. Okay. So, that means what? So, that means this is actually the curl of F. If I write it another vector field G, that means this is actually the field G has a what is called vector potential, and what is my vector potential is capital F. Okay. So, if I calculate the divergence of curl of capital F, where capital F is a C2 vector field, then which is nothing but this del operator dot, this is my curl del cross F, and if you calculate it, it turns out to be 0. So, of course, the proof I have given. So, suppose F is a capital F is a vector field from R3 to R3, that means this is my component F1, F2, F3. So, if I calculate the curl of F, so these are the components. So, this formula you can have it, na, I cap, J cap, K cap, then you have del del x, del del y, del del z, and what will have? You have the component, right, F1, F2, F3, right. Using that formula, so if I do that, so of course, I have written, I think this is D1. This is D2 and this is D3, okay, in that way. So, the first one we have to calculate the curl, which is nothing but component of, this is the component of I cap, this is the component of J cap, and this is the component of K cap, not an issue. And you just take the divergence, I mean you have to take the dot product. So, that means first you consider del del x of this object, then del del y of this object, and plus del del z of this object. You just do the derivative, and most importantly that capital F is in C2, that means all the second order partial derivative they exist and they are continuous, that means the mixed partial derivatives are equal, that is very important. Once I have that one, you see D21 F3 which is same as D12 F3, so I mean this should be 0. D13 F2 minus D31 F2, that is also 0, and D32 F1 minus D23 F1, that is also 0, because my capital F is in C2. In other words, all the mixed partial derivatives they are equal. Of course, all the mixed partial second order partial derivative they exist and they are continuous. So, therefore, mixed partial derivatives of course they exist and they are equal. So, therefore, this is 0, this is 0, and this is also 0. So, if I calculate the divergence of curl of capital F, it is 0. Theorem, provided capital F has to be a C2 vector field, that is very important. That means I need to have this condition like all the mixed partial derivatives they exist and they are continuous, so that I can have the equality of any two mixed order partial derivatives. Okay. There is another theorem. What is that? So, if a vector field capital F in R3 has a vector potential, then divergence F is 0. So, just now I said, okay. So, like if I have a vector field which has a vector potential, what does it mean? That means that there exists another vector field G such that your vector field capital F, which is nothing but curl of G, right. That is the definitions of what is called vector potential. So, if a vector field capital F has a vector potential, that means capital F which is of the form curl of G. Now, I want to calculate divergence of F. What is that? Divergence of curl of G, and what is divergence of curl of G? That is 0. Just now I have observed, na, divergence of curl of F, provided of course F is nice, that means C2, and that is exactly the case. So, okay. So, this is my proof. Since capital F has a vector potential, that means capital F I can write curl of G or del cross G for some vector field G in D by using the result proved in the previous slide. It follows that on D divergence of F, which is nothing but divergence of curl of G, and which is 0. Of course, here I am assuming my capital F has a vector potential, that means the vector field I am getting G, which is nice, I should say. Nice means what? That means it is a C2 vector field, right. G is a C2 vector field, so that if I take the curl of G, it is the vector field capital F, and if I take the divergence, it is 0. So, that is the conclusion. Okay. So, this is simple example. If I capital F, this is my vector field, then divergence, if I calculate, this is non-zero, therefore, I can, of course, this theorem says that F does not have a vector potential, because if capital F has a vector potential, I just say that then if I calculate the divergence of this vector field which has a vector potential, it has to be 0. But now if I have a vector field whose divergence is not 0, that means it automatically implies that that vector field you cannot have a what is called vector potential. Because if it has a vector potential, that means if I calculate the divergence of that vector field, it is 0, but it is divergence. For this example, divergence is non-zero. So therefore this vector field capital F does not have a vector potential. Okay, it is just the applications of the earlier theorem. Now I talk about what is called the definition of Laplace operator. What is Laplace operator? The Laplace operator on Rn, I am denoting as what is called del square, and it is defined by del square, which is del dot del. Okay. So, I mean, what is del? Del x1, del x2 up to del xn. So, what is del operator, if you remember? So, this is del x1, del x2 up to del xn, right? So, what is that? This is dot product. That means this should be del 2 square del xn square del x1 square plus del 2 square del x2 square up to del 2 square del xn square. This is called a Laplace operator. Okay. So, now for a scalar field, if I take a scalar field phi from some domain D subset of Rn to R, then the Laplace operator, which I denote it as del square, applied to my functions phi, that means del square of phi, which is nothing but you have to consider this object. That means you first perform the second order partial derivative with respect to x1 variable twice. So, del 2 phi del x1 square, then del 2 phi del x2 square up to del 2 phi del xn square. Okay. So, and if I just equate to 0, the partial differential equation del 2 square phi is equal to 0 is called the Laplace equation. So, this is the Laplace operator. If I say that del 2 square phi is 0, then it is called the Laplace equations. Okay. I think it is clear the definition of Laplace operator and the corresponding Laplace equations. So, Laplace operator means you have a what is called del operator, you have to just take the dot product of two del operator, same del operator del dot del, which will give you operator, that means del 2 square del x1 square up to del 2 square del xn square sum. So, if I act on any vector phi, nice. So, therefore, del 2 phi del x1 square up to del 2 phi del xn square, and if this equal to 0, then it becomes a Laplace equation. If a function phi, which is a scalar field from some domain D subset of Rn to R, and if it satisfies this what is called Laplace equation, then I am saying that phi is called a harmonic functions. So, functions phi, which is a scalar field from some domain D subset of Rn to R, if it satisfies my Laplace equation, that means if del square of phi is equal to 0, then I will say that this phi is called a harmonic functions. Okay. Couple of identities. This is the last slide for this concept. So, let G is a map, or G is a scalar field from Rn to R. Of course, I assume that it is C2 scalar field, then twice continuously differentiable. Then first thing is that if I calculate the curl of my gradient vector field grad of G, this is 0, and if I calculate the divergence of this del G, it is actually del square of G, that means del cross of another one. This is that first one, divergence of del G is 0, and this is the curl of this G del G is also 0. Okay. So, these are the properties, and this is comma. So, there is a gap. So, you can bring it back to here actually. Okay. So, these are the properties. So, that means if I have a C2 scalar field, curl of gradient of G is 0. Now, you can calculate it. You just calculate it. First, you calculate what is the gradient of G, and then you just calculate the curl, because you have all the formulas are there. You will say that. Of course, this fact will be very much useful. That means C2 scalar field. That means all the second order partial derivative, they exist and they are continuous, and which will tell you that the second order partial mixed derivative should be equal. That is very important. Okay. So, then curl of grad of G is 0, divergence of grad of G, which is del square of G. Then if I consider G del G, then if I take the del operator cross, that means curl of this, then it is again 0. Not only that, if I have two say vector field capital F and capital G, two vector field with the assumption that they are C2, then these are the formulas are true. That means divergence of curl of F is 0, divergence of F cross G, this is nothing but curl of F dot product with G minus curl of G dot product with F. Curl of this vector field capital F cross G, which is capital F times divergence G minus G times divergence F, then G dot del F minus F. These are the formulas. You just calculate, use the formula, the curl, divergence, gradient, you will be able to get it. Okay. Curl of curl F, if I calculate, this is gradient of divergence of F minus del square of F, gradient of F dot G, which is vector product of a capital F then curl of G plus G cross curl of A plus G dot gradient of A plus F dot. Anyhow, these are the formulas. So, these formulas are very well known formulas. So, if you know the concept of what is called gradient, divergence, curl, Laplace operator, then you will be able to prove all kind of stuffs. Okay. So, maybe if I give some vector field and I say that calculate like divergence of curl, or say curl of this cross vector field F cross G, or say curl of F, you may use this kind of formulas. So, you may use this kind of formulas to conclude, okay, this is the corresponding object. So, that probably one of the advantage of this kind of formulas. If I give some vector field and say that, okay, calculate, suppose you calculate curl of F cross G, suppose you know the divergence then or gradient, then you can calculate curl of F cross G, like you know the divergence, you just calculate F of divergence, G divergence, then G dot del F. So, just that is it. Okay. So, F of divergence of G, suppose you know the you know how to calculate the divergence. So, once you know the divergence, then capital F of divergence of G, G of divergence, and then take the dot product of G of gradient of F and F of gradient of G, you will be able to get what is called curl of F cross G. So, these are the formulas. So, there are some problem you can calculate through these formulas. Okay. So, I think I should stop here. So, these are all about what is called concepts of what is called gradient, divergence, curl and Laplacians. Of course, I am not saying these are all, there are many, but at least for our purpose I think that is enough. Okay. So, I think that is all for this concept. I think next class I will talk about some new concept, what is called, like say, as I said, this lecture I talked about like vector line integral, right, okay, or kind of line integral, vector line integral, or so this kind of concept maybe I will talk about in my next lecture. So, next lecture onwards there will be something new, like means the concept of line integral or vector line integral or surface integral. So, that at the end I want to talk about what is called divergence theorem and Stokes theorem. Okay. So, I think this concept I am kind of completing in this lecture. So, next lecture I will talk about integral. Okay. Integral means that, of course, the Riemann integral, double integral, triple integral I already talked about. Now, the vector line integral I just said a couple of times it occurs here, right. So, those are the concept I will start in my next lecture. I think I should stop here. Thank you.